Hello everyone, welcome to another SSY seminar. Today we are introducing Professor Bill Langdon from UCL from the CREST Center. So Bill has been working for a very long time at UCL. He even did his PhD there. He was also at XX, working for a period of time, moved to King's, if I remember properly, and then when the group moved back to UCL, he moved, I think it was in 2010, 2011, more or less.
Long time ago.
Long time ago. And they've been working at UCL since that. His major contributions, apart from the field of genetic programming, who is one of the major names who have contributed on genetic programming, is also to the field of genetic improvement. Bill has been one of the founders of the field, also one of the people who has contributed the most to improve software by using evolutionary computation in terms of identifying different ways to make software more efficient. And today he's going to talk about something slightly different, but slightly similar. That is basically how information theory and robustness can support us to understand our software and to hopefully improve it. So, Bill, the floor is yours. Thank you for coming.
Thank you, Captain. So I changed the title slightly from the abstract that was distributed. So this is going to concentrate more on software engineering side. So various things have been left out in terms of timing and so on. So slightly different title. I'm going to skip past the applications of genetic programming and creativeness of genetic programming. And what I want to do is concentrate more on some experiments with GP where we ran the GP out to 1 million generations. Principally because we could, but also what was learned from that. And then explaining the results from GP in terms of information theory, and in particular, the failure of disruption, whether it's mutation or an error or some external adversary injecting faults into software. Looking at that disruption, how it propagates the output, or in particular, when it doesn't propagate the output. So taking lessons from very deep GP trees. And then the second part is seeing, well, that's true in hierarchical systems. How much is it true in real pieces of code? So there'll be two examples, one in C and one in C++, of very deep code where we mutate it and see what happens. And the upshot is, the deeper the code is, the more robust it is. So if we inject faults deep within the code, there's less chance of those faults being visible externally. The implication of that is, if you want to find faults, then you're better off looking at shallow bits of code. And in particular, in our case, that usually means doing unit tests rather than complete system tests. And so in terms of testing or improving or optimizing or even fixing bugs, it's much easier in shallow code rather than deep code. Oops. Okay, so I'm going to skip these parts. So the background to this is Richard Lenski, pretty much as soon as he finished his PhD, proposed, so this is 37 years ago, proposed running an experiment where bacteria were put into very stable environment to see what happens, see how much evolution there is. And the wisdom at the time was, why bother? We know exactly what's going to happen. We know that the bacteria is going to evolve to suit that environment, and then evolution will stop. But he ran the experiment anyway. And he's been running this experiment for 37 years. And now out to 80,000 generations. For comparison, Homo sapiens is about 9,000 generations old. And the upshot was the experiment showed that the bacteria continue to evolve. So all the experts were entirely wrong. And the point being, sometimes it's worth doing things which on the outside seem impossible. What I did, and what you can do, is run an artificial evolution system. So again, in a very stable environment. And here we ran it out to 1 million generations. Takes a while, but not in comparison to 37 years. The runtime, sort of about certainly weeks, maybe half dozen weeks. I say days or weeks because the system got progressively faster as I got more frustrated with how long it was taking. So you're going to see lots of plots here with log graphs. So be wary of whether these are log scales or not. We're minimizing, so better is lower down. Each of the colored traces there is a different run, a different population. And what I want you to notice is, firstly, in all cases, the population improved. The numbers up the side here are the numbers of improvements in the runs. So typically several thousand improvements. The thing that's disappointing from my point of view with the experiment is, although we get some nice traces where evolution keeps coming in and keep getting improvements, in most cases we get a long flat tail. So there are cases where the rate of improvement just falls away. Some bit in the foundations of genetic programming, which is copied there, there's a prediction that populations, GP populations, should evolve to meet this parabola. So this is a parabola which says where the center of the search space is. And it's, although I put it a parabola on the log-log graph, it's a straight line with a slope of a half. And each of these dots is from a different run. So the different runs are given different colors, but you can see over time, not only do the trees get bigger, radically bigger, but also they get deeper. So we're starting off with populations down here. Over time, they're moving more or less along the diagram. So they're not only getting much bigger, but they're getting much deeper. So what this plot is doing is we're looking at the last 90% of the run. So interesting dynamics early on is ignored. And we're also plotting averages. So if you don't plot averages, you just get a mess. But if you plot the average over, I think we're averaging over about 100 generations, you get these more or less straight lines. So what we're doing is we're plotting the rate at which the population improves against the reciprocal of the size. So as the trees get bigger and bigger, we actually move down towards the origin. And at a rate which depends on the run, so we also decrease the rate at which we're finding new improvement. The different runs are in different colors, and you can see there's different dynamics in each run, but we're always ending up down in this origin, which is exactly where we didn't want to be, because that means the populations have become stable. The explanation for that is simply there's a fixed target area within the tree, which if we change that target area, then we're likely to change fitness. If we're outside that area, then it doesn't make any difference. And as the trees get bigger, the fraction of ineffective parts of the tree just increases in proportion. So this is why we get that nice dynamic. Those experiments I've been talking about, the floating point. Here's an example in an integer problem. What I'm doing here is I've deliberately chosen a fairly small solution to the Fibonacci problem. So this is a tree that was evolved. We treat this as a fixed tree after the evolution. And the way GP works is we perform calculations down on these leaves, and the calculation propagates up through the tree until the answer pops out at the top. So you'll see trees like this where the actual output, the root, is from the root node. What I've plotted here is we take the fixed tree, we run it, and at some point in the evaluation, we make a small change. Here, we're just adding 1 to the evaluation. So whatever value there was here, we add 1, and then we see to what extent does that change propagate through the tree to the output. In the case of the colored nodes, particularly the red nodes, if I make a change here, it means in more than half the test cases, we get the wrong answer. So here, if we change it at runtime, we break the answer. The blue nodes means if we make a change at one of the blue nodes, we break one of the test cases, but the other 19 are still producing the right answer. The point being, the vast majority of this tree is all white. We can make a runtime change, small runtime change, on the vast majority of the tree, and it has no impact on any of the test cases. So this is essentially the same plot, but the different colors are for different runs, different individual trees. And what I'm plotting here is the distance from the disruption to the root node. So how many levels in the hierarchy the disruption needs to propagate before it gets the answer. So if we start off very close to the output, there's a reasonable chance that a disruption of +1 will have an impact. This question.
Can you remind what every node in the tree means?
I have not really explained. So the nodes in the trees are calculations. So it might simply be, we take the value coming from this side and add them together and then propagate that addition upwards. So this is, as I say, is an integer problem. So everything in the tree will be have an integer value. From memory, I think there are plus minus times. Don't think there's division in this particular example, and there are some special ones to handle recursiveness.
So the entire tree represents a program.
Yes. So
it actually represents an expression.
Yeah.
It's a very large integer expression, numerical expression with operators. So each subtree is an operator.
Yeah, you could think of this subtree as being a function of these inputs.
They're asking, sorry, is index trees or non data flow graphs?
Nine. As David said, they're expressions. And because everything in this tree is a binary function, the tree is a binary function, binary trees.
And so it's an expression with some free variables or everything there?
So the way the values come in, they come in through the leaves. So the leaves are the inputs, and then the internal nodes are very simple arithmetic functions. So this is here we're looking at multiple runs, different colors, but all having the same sort of tendency. And that's with a minimal disruption at runtime. If instead of making a small change to the evaluation, we make a large change, we totally randomize it. So Whereas before it produced an integer, now we replace that integer with a random value. So a large change, we see exactly the same thing. So again, an exponential fall off. Each of these crosses is an average, but the straight line is an exponential fit. Not only exponential, but it's also rapid. So we're reducing probabilities by about a factor of 2 every time we go 2.3 levels that way. So you can see if a tree is 4, 5, 6 levels deep, we're already got a fairly small chance that the disruption will make any difference externally. And as we get deeper and deeper, there's almost no chance that a large disruption is going to be visible. So
It's number of levels related to the structure of the Fibonacci, because like the way of the implementation make that, like if it's more than 3 levels, we will not see the change. But is it the case for like every program or other program as well? Or could it be because of the way the tree was constructed?
So GP tree structures have been used on many, many different problems. So although I'm showing you something that's specific to the Fibonacci problem, it could have been, in principle, any problem.
But it would be the same level, or for another program, it could be, I don't know, 7 level.
Oh, no, you're exactly right. Yes. So here, the fall off is about a factor of 2 every 2 and a bit things we go deeper in the tree. In the case of the floating point examples, it was more like 7 levels. So yes, that does depend on the problem and the representation.
But in all of them, you see that at some point you have one level that 1 or 2 level where under which you cannot see the error, and under which you kind of say.
Not that you can't, but it just becomes very unlikely.
Yeah, exactly.
So that is an artificial evolution system. It's a very pure hierarchical system. So what we want to do now is say, well, okay, reasonably confident this is going to hold in anything that doesn't have side effects, where information only propagates up through the tree. Does the same sort of thing hold in real programs? And the answer to that is, of course, sort of. So recap of, I guess, Boas's Pi framework. So essentially his argument was, if we have bugs in the software, that bug needs to be executed. It needs to make some change to state. So not only does it have to execute, but it has to change the program some way internally. And in particular, that internal change needs to propagate to the outputs. And so what we're looking at is ways in which the disruption can fail to reach the output. In other words, that the bug, or indeed any other form of disruption, becomes invisible, as simply because the disruption it causes does not reach the output. Yeah, we've just seen that in GP trees, they become robust as they get deeper. We're going to look at a couple of benchmarks, one in C and one in C++. In terms of information theory, everything inside a computer is an irreversible operation, meaning from the output of an operation, we can't infer what the inputs were. So here I've tried to show this as a schematic with a funnel. So we're taking 2 floating point numbers, up to 32 bits of information in each of them, so up to 64 bits of information going into our funnel. but coming out, we've got a single 32-bit number. From that 32-bit number, in general, we can't infer what the inputs were. So we've got at most 64 bits going to at most 32 bits on here. So I've tried to describe this this entropy loss in terms of a funnel.
But that does mean generally, not reversible, right?
You can devise examples where you would know what the answer was if you.
Yeah, I just check.
Yeah. Yeah, you could do it with XOR.
Exactly. Yes.
But if you've got two inputs coming in general, you lose information.
I agree.
In a hierarchical system, if you lose information at any point, you can't recover it. So if we get to the output and we lost information here, then that's gone. And what the red arrow is trying to show is if we have some form of disruption here, whether it's a bug or some sort of malicious intent that changed the input here, it may be diluted as we go through the network. And in a purely hierarchical system with no side effects, once that information is gone, it's gone. And when it's gone, that disruption can't change the output. So that disruption becomes totally invisible. Okay, so we're going to try and see to what extent this happens in real code. The first example I'm going to talk about is from the Parsec suite of benchmarks. It's the BIPC image processing library, total of about 90,000 lines of code. What we're going to do is take a piece of code which takes a large image and produces a thumbnail. And in this example, I carefully removed all the lines of code which are not being executed. So we go down to about 7,000 lines of code, and we're going to throw 1,000 mutations at those and see what happens. Oh, sorry, yeah, large image thumbnail. So the first thing, which might be a surprise, is most cases, 1,000 mutated codes compiled, they ran, and produced the right answer. Most cases. You've got a large number of cases where it failed to compile, which is kind of irritating since Magpie is supposed to produce compilable mutants. Only 16% did the code run and produce the wrong answer. Most of those cases were exceptions, so it actually failed. We're going to exclude those from our discussion because there's an exception. The program effectively stops. The disruption doesn't get the opportunity to propagate out. So in the first case, we got 37, which is 3.7% of bugs which run, they cause a disruption, and that disruption makes some change to the output. It could only be a single bit change, but we were very definitive about either produces exactly the same answer or it doesn't. If it doesn't, it's failed. So we got 37 of those. What I did was to choose at random 25 of those and instrument them. So we know exactly how deep it was when it was executed. And we're going to do a pair comparison against 25 cases, again chosen at random, where the mutant was executed. It did make a difference locally, but that change didn't reach the output. So we're going to compare those 25.
25. Yeah, 25 from this one and 25 from this.
Yeah.
Okay. Just be sure.
Dan?
Are you saying was the correct output, it executed that mutated state. Definitely executed that.
Oh, yeah. So part of the selection was ensuring it was executed, ensuring that it did actually make some difference. So it's not a silent mutation.
It's
So
weakly killed.
I'm sorry, Dave.
It's weakly killed.
Yes,
It's executed in fix.
in the mutations.
In the mutation lexicon.
Yeah.
Mutation testing lexicon. Call it weakly killed.
So we know that the mutation has happened. We know it's made a difference, but that difference hasn't propagated to the output.
Can you just an equivalent mutant? Yeah, an equivalent mutant. Semantically speaking, I mean, maybe it make a syntactic change, but
Okay, so I try to be very clear about what I've done. It's obviously not equivalent locally,
yes,
but and I haven't proved that it's equivalent in all possible test cases. On this particular test case, that change occurs, but it doesn't reach the output.
but it could be semantically equivalent to the original.
Imagine that you are adding two numbers, like 2 plus 2, and multiplying 2 times 2. That mutation of plus and multiplication change the output. It doesn't change the
It
output
doesn't
in this
change
case,
It
but
change the code,
it
but
changes the semantics here.
Yeah.
But in this test suite, it's not changing the output, even though in other test suite might change the output.
But
It's the other way around.
it's more general than that. It's more general than that because you can have like take one program with two different implementation of the same program. Those
Yep.
implementation are perfectly equivalent semantically with every input possible.
Yep.
But they can be seen as mutant of each other, but they will always produce the same output. But it's not really a bug. You cannot see it as an artificial bug because it's not a bug, it's just different implementation of the same thing.
Okay, so what I'm saying is there's a local difference, and that local difference has been exercised. It does make a change of state, but that change of state doesn't reach the output.
Doesn't propagate.
It doesn't propagate.
So it's
So
it's not a syntactically mutant, but it could be a semantic one. I think.
Yeah, think about it, it's like the small step semantics might have changed, but big step might not have.
Yeah.
If that makes sense.
Yeah. Okay, so we're going to do a comparison between 25 where the disruption reached the output and 25 where it didn't. And what we're concerned about is the depth of the execution. Oops.
Back to the left.
The thing is, in one sense, you can have maybe just that we didn't choose the one input that can show the implementation. Yeah.
So what we plotted here, so we have two classes. The red ones are the cases where failed disruption has occurred. The program ran and produced identical answers. So that's these red cases, some of these here. The blue ones are where the mutation occurred and it's changed the output in some way. But at least the program ran and the disruption had to work its way to the output. And all I want you to take away from that is once we get very deep in the program, the chances are our mutations are likely not to make a difference to the output. Here we can see that there's a very dramatic difference. That's our first benchmark. The second one,
Until
yeah.
you go back one slide.
Yeah.
See, just past 50.
There is a blue guy there, yes.
It's probabilistic, right?
Yeah, it's probabilistic. But You remember? Surely you remember that one.
That's it. Somebody who was
Put your
executed.
finger down. Flat finger.
Was executed. So this is in terms of executions. So that's probably been executed about 15 times. And one of those, at least one of those executions has made some difference to the output. So you can see some of these are executed a huge number of times. I mean, they're in some loop that runs many times.
Besides
The guy who wrote the code.
So if you had more data, would you expect this? What would you expect the shape of this to look like? Because at the moment, I've got some sort of with Bluebit, like vaguely normal looking, but I would assume it would be some sort of exponentially decreasing from that way.
Well, bear in mind this is handwritten code.
Yeah, indeed.
So in terms of you've got confounding factors like how deep is this sucker? And it's not just depth in terms of syntax, but depth in terms of the calling hierarchy. It'd be an interesting question of if anybody's got any statistics on what that distribution follows, but I've not seen anything very general. I would expect there'd be a very asymmetric distribution, but that's me guessing rather than having seen it.
Thank you.
Yeah.
Some functions may be called multiple times.
Oh yes, yes.
So how, and then the same function has in the same run different call nesting depth.
That happens, yes.
And then what do you do? How do you put it in the graph
I measure the execution depth
each time?
each time. So some of these bugs, some of these mutations, sorry, execute at different depths. I think there's an example which runs at a depth 10 and something like 20, and the execution is shared between those. So sometimes it's much deeper than others. I mean, it happens. It's real code. The other example is C++. It's Gem 5, which some of us have worked on. The point of the graph is really the depth of nesting runs up vertically on the profile. And just to highlight that there are some parts of this code which are very deeply nested. So the top of there is about 80 levels deep. And some of it here is more like 4 or 5 sort of typical things. We're going to do the same sort of thing here. I was not so clean about ensuring the mutations occurred in executed code. So although we threw 2,500 mutants of code, in most cases the mutant ended up in code that wasn't used. So I'm just going to ignore those. And look at the cases where, look at the remaining cases. Again, we have a large fraction of cases where the code compiled, ran, produced the right answer. We also have an annoyingly large number of cases where it failed to compile. And again, a perhaps surprisingly small number of cases where it ran, it compiled, it ran, and produced the wrong answer. Again, wrong answer means any part of the answer is wrong by even a single bit. Most of those are exceptions. So seg faults, internal errors, cases where the mutant caused the program to stop dead rather than the error propagate the output. But we have, in this case, 55 mutants where we're going to trace their execution and in terms of depth and the output. Again, we're going to choose 25 of those at random, and we're going to choose 25 from the mutants which didn't cause an error. And again, we do a comparison between those two sets of 25.
Yeah, can I ask, what
Oops, sorry.
you say output, what is it that's being?
Gem 5 is much more complicated than the thumbnail example. Gem 5 produces about 5 different summary files. So stats about the execution of the program. And there are about 5 of those files. So any one of them is different in, except for timestamps and irritating things like that. Different in any tangible way, then we say it's failed the test. So yeah, so timestamps
String.
string comparison, yes.
So you said the failed to run correct was a relatively low number, but that looks like 20% of the ones that actually ran. That doesn't low to me.
No.
So what's your definition of low?
Well, of the ones that ran,
So only 800 of them.
Okay.
Well, 800, then 228. So basically 397 and 145 are the numbers I care about, right?
okay.
Tell me if I'm wrong, but am I misreading this in terms of what's the most interesting information?
Well, I guess first off, to me, there are a large number where you couldn't detect the error.
Yeah.
Of the ones where you can detect the error, most are blindingly obvious because it's segfault.
Right.
And it'll produce an error message and say, go away. And then a relatively small fraction are where the mutant propagated outwards.
Okay.
And so again, we're doing our comparison between 25 in each class. Again, the red ones are the cases where the program appeared to work despite the error within it, or despite the mutation within it. And again, there's above a certain depth, there are, so again, this is a log scale. There are cases where lots of mutation executions do not reach the output. Below maybe 48 or so, there's fairly wide mixing of the answers. But in the deeper ones, there's a fairly clear case that if it's deep within Gem 5, it's unlikely to reach the output. Sorry.
If I can conclude from that, my program only nests 19 functions deep, I will have no bugs.
I didn't sample this extensively.
But I think there's an interesting point. So the data that you've got from 20 onwards is that's exponentially increasing roughly, but roughly different sampling bias. So then what is our theory for why we see very little below 20? I don't think that's just sampling bias. I think there's something deeper going on there. I'm curious what the thoughts are. Is it the nature of programs that the top level things are heavily tested, or that they're very boring?
I would still hesitate. We've only thrown 2,500 mutants in this code, and it's 1 million lines of code.
I would not be surprised if we see this replicated at a higher scale. I don't know if the exact numbers are 20. That would be very interesting, I think.
Yeah, okay. It would be interesting to see a map of how well this code has been tested. I suspect somebody somewhere has actually done studies of that, but I haven't seen them. I mean, you could potentially look at outputs from the fuzzing campaigns in terms of, hey, the trace went through these levels of nesting. but I haven't seen that done. Yeah, you might be right that here it's within the scope of a programmer to look at all that code. Whereas here we're looking at 900,000 lines of code. Dan,
That seems really deep in terms of.
that's partly why I chose this example.
Yeah, I'm intrigued. What do you think, like a average program or the other programs you looked at? How deep do they normally get?
Short answers, I don't know. It's obviously the bigger, this is a feature of big systems. So if you take your traditional benchmarks, get anywhere near here. I mean, a deeply nested triangle program, 3 levels. So that's why, I mean, one of the reasons for choosing it was it's real code. It's well tested. I thought well tested. It's known to be deeply nested. I suspect Laurie's right in that there is some general distribution that you would expect, which might vary between programming languages, but not much. Where as things get bigger, they also get deeper. Maybe at some logarithmic rates, but I'm hand waving very heavily there.
So that plot there is showing just for one input, or is it across lots of different inputs?
This was a Gen 5 run.
Yeah.
So it's a I should explain. Gen 5 is a simulator. What it does is every instruction in some target is simulated exactly. So it does things like, oh, this needs an operand. I will go to memory and get the operand back. I will work out how long that process is going to take, how long the cache is going to be idle until it hits it. When that hits the cache, then I will release the next part of the processor. So although the benchmark is not very big, I think it's about 1,000 instructions or so. Each of those causes a huge amount of computation to be done within Gen 5.
Sure.
And the way Gen 5 is structured, I think is partly responsible for why we get very deep things.
So the question is, so that sounds like it's some kind of simulator, but it takes an input program to execute.
And it should be deterministic. It's deterministic in the sense of each time I've run it and look at the outputs, they are mostly very similar. But in terms of the order in which events actually occur inside it, they do occasionally differ, which I suspect they shouldn't do.
I'm wondering if you were to give it differently, if that's all for one input, you give it different inputs, and the distribution is different. You might have a load of bugs for like 20.
Yeah, maybe. But I think you're going to see something similar.
Okay.
Not identical, but something similar. And yeah, it becomes then a question of feasibility. It's probably better to spend the effort looking at another program rather than looking at this one multiple times. So that's really to satisfy the reviewers that we do have a p-value. Okay, so to conclude, I've skipped past the point about GP being in use and being creative. The schematic is supposed to be a GP generating patterns as fast as the guy can actually log them. From an AI point of view or an A-Life point of view, what I concluded from the GP experiments was we shouldn't be trying to evolve a huge tree. We should be trying to evolve more like a forest or a mango swamp, where each of the trees is itself shallow, but the whole forest is how we calculate our answers. In terms of generality, I'm quite convinced that in a nested system, information theory will apply. You are going to get entropy loss. You are going to get failed disruption propagation. The point of looking at real code is we see something that's not as clean, so we don't get a nice exponential fall off, but we see a very strong relationship to depth. I put notion here greater than 30 depths of nesting, but I think that's going to depend very much on your programming language, your programming style, but something like that. In terms of software engineering, what we should be doing is looking at testing of shallow code, which in practice means unit testing. So looking at small pieces of code, which by definition will be shallow, rather than there's a small explosion in the rear there.
Surely system testing finds faults that unit testing doesn't.
Why?
I don't know. I prefaced it with surely.
Okay, so I'm not saying that you shouldn't do do system testing, but I don't think there's any point doing system testing
Be saying,
until the unit tests are passed. Sorry?
You seem to me to be saying, let's abandon system testing.
If you've got a limited amount of testing, then you're better off spending it on your tests. Be my suggestion.
In a way, but I think the bugs you find with unit testing and system testing are not at all the same. Because here you are focusing on mutation, and mutation works great with unit testing. That's the thing that's usually done. But with system testing, we will also see the problem arising from combining components together and integration testing as well. And I think that's two very different types of bugs. And here you are not looking at integration. I mean, kind of, but the mutation is something local, so it doesn't really have an impact on the integration of the components together. And I think that's why you don't see it when a big problem.
Yeah, it might be in integration testing. You're taking code written by different people, and that interface produces a whole range of different bugs that you might not get in code that's written by an individual.
That could be one of the reasons, but I don't think it's the only one.
Okay. Okay, maybe this is too strong, but in terms of the effectiveness, I suspect when you've got a deep system, if there are bugs within it, it would be easy to find them if you could move to unit testing. So if you have a way of looking at the system, internals of the system, and testing the internals, rather than testing the whole thing externally.
There's a question behind you.
Yeah.
Oh, sorry, Hector.
No, I was following up on Sophie's point. I think in terms of priority, I would give much priority to a system testing bug, especially because sometimes in unit testing, I mean, the system in terms of integration limits the way that you are using the specific functions that you're going to test with unit testing. A division by 0, for example, might never happen in system testing if you limit the value of the divisions. But at unit testing, you might find it because you are not doing that inside of your unit test or in your function, I mean. So I think following and supporting Sophie's points.
For me, you need both.
Yeah.
I mean, usually you start
save
with
time.
unit testing because it's
Always
easier to
He
do.
hasn't said don't do unit testing.
It's
Nah.
easier to do, and it can like obvious bugs, but bugs that will be a problem anyway. So I think it's always good to start with unit testing, but I don't think saying that system testing are less useful than
also faster, so normally focus
Yeah.
on system testing. like we did with Xerxes. So
May I suggest a variant of your penultimate bullet point about shallow unit tests? I think what you've shown is that if you unit test functions that are only ever deeply nested, you'll find a ton of bugs in them when you look at them directly that will never manifest at top level. So you'll fix them. Your code will be less buggy for the unit test, but you will never notice them at the top level.
Potentially.
I mean, probabilistic.
And you then release it to the users, and a thousand users find the bugs.
Indeed, but I think that's what you've shown. You've shown that a whole load of bugs stuff. So I could spend ages fixing function ADCF that's buggy as hell in isolation, but in part of the system, those bugs can never be reached because of the entry. That's, I think, is what you've shown.
Yeah. I mean, not necessarily can't be, but
Or you do a very specific input. It's like your blue. You had a graph with a red, blue, and white nodes, and it's like if you are in the blue, in one of the blue nodes, you told that only one input can reach this bug, and in system testing, the probability that you use this exact fine input showed that in practice you will not see that bug. But it doesn't mean that the bug is not present. So those blue nodes are easier to correct and to find out with the unit testing, probably.
But there are some unit tests that find bugs you can't ever reach. That's what he's shown. Or there's such a low probability that the probability may go to 0. So if you spend lots of time unit testing those, you waste your time. I think that's
a good point. Yeah.
That's yours for free. If you're co-author of this.
actually, there's something that, considering the new era of generative AI, they are going to take both for training and unit testing level, which means that if you ask a generator, a code generator, to generate something, it will do it at unit testing. If it has learned with unit cases that has not been properly tested, you are supporting here. Actually, you might be introducing new codes in your new bugs in your code that in the code that was used for training the AI was not relevant, but it is in the code that you are actually reading. So actually, you have a point for the current programs with generative AI.
So if I think of it like taking something from Stack Overflow, the AI has generated something that you might think of as
perfectly functional. Like, for instance, I was asking for the curve Kleibler divergence, and it forgot that when the value of the denominator is 0, it doesn't have to calculate it because obviously it's a division by 0. So yeah, those bugs are there, and they might propagate because they didn't consider that maybe in the program that they're using for training the AI.
Maybe David's got an answer there.
No, I've got another question. I wasn't even listening to it.
Oh, that's
I don't know, can you guys hear us at all?
What was your question?
What happens if you increase the number of tests by an order of magnitude?
I don't know, I haven't done it. So in terms of, I mean, to take Laurie's point, this is probabilistic. So you might not get nicer, smoother graphs, but I'm fairly sure.
I'm more thinking, okay, let me be a little bit more you've got somewhere in the slides there some kind of, on the basis of some of the diagrams you've showed us, there were suggestions of some kind of relationship between the amount of nesting and the likelihood of failed. But do those numbers stay the same if you increase the number of test inputs by, say, 1 magnitude?
So I haven't done it.
Yeah.
Well, I mean, these Okay.
What if we increase it by 2 magnitudes? Or 3?
So this sucker, this mutant has been executed 200,000 times. So, and it's failed on one of those, at least one of those. This one's been executed 200 times, and none of those have propagated.
Yeah, but it's a fixed test suite.
Oh yeah, yeah.
So obviously increasing the changing the test suite, or even worse, increasing it by orders of magnitude might change the diagram. I mean, I think the general point will, my guess is that the general point will remain. You'll still get diagrams like that. But the depth of nesting that you observe.
In terms of the cutoff here.
Yeah.
Quite possibly. And I think the cutoff point is going to be very much dependent on the program you're testing and possibly also the test suite.
Yeah. There's going to be a lot of parameters. That's
and difficult to know in advance which ones are going to be important. But yeah, so prolonged testing you would expect to find more things, but I'm reasonably confident we're still going to see some sort of long tail of stuff that doesn't reach the output. One of the things I did do was to look at why. So look at some of these cases where mutations occur, state changes, but that doesn't propagate. Most of them were very specific to the code of the test. There were some things that came out repeatedly. Multiply by 0 is a very good way of squashing errors.
Yeah.
That came up several times. And the other thing that came up repeatedly was leaving the scope of a function. So your mutation did some change, propagated the variables within that function. When returned from the function, all that disruption gets left on the stack and ignored. So multiply by 0 and leaving scope with the things that occurred multiple times as ways of, as mechanisms for causing further disruption propagation. Other ones were very specific.